In this lecture, we're going to review Module 11, Lewis dot structures, and we are going to add to that concept. We are going to look at some compounds that are exceptions of the octet rule. Pretty much everything we've done has obeyed the octet rule. The structures of Lewis that we represented all had 8 electrons around the central atom. We'll see that some structures do not obey the octet rule. And we will tie in shapes, molecular shapes, with these Lewis dot structures. And I brought some models in order for us to be able to understand these. The basic concepts that we have seen from Lewis dots. First, we need to know how to do Lewis dot structures of elements. And in order for us to do that, we need to look at a periodic chart. And in a periodic chart, anybody in group 1 has 1 dot, anybody in group 2 has 2 dots, representative elements. For representative elements, look at the group number, and the dots, or the valence electrons, are equal to the group number. So anybody in group 7 has 7 dots, 7 valence electrons. Anybody in group 5 will have 5 dots. That's for elements. Then when these elements mingle and form compounds, you can have either an ionic or a covalent compound. In an ionic, electrons transfer, like sodium chloride, and in a covalent, electrons are shared. Okay, so the verb to transfer or to share is essential to understand the difference between these two. Sodium is a +1 ion, Cl is a -1 ion. They are not sharing. That is not a covalent bond. That is an ionic bond, and we have seen structures of many ionic compounds as opposed to covalent compounds. Okay, so these were all ionic, and then we move to covalent. Quick review on covalent. We first draw the most symmetrical structure. We check the dots for each element, and then we finally try to obey the octet rule, if possible. You start there. We're going to see that sometimes the octet rule is obeyed. So yes, the octet rule happens. Or there are compounds which are going to be exceptions of the octet rules. We'll look a few more today. Our first example was CH4, and we said that CH4 had carbon with 4 bonds, and the 4 bonds came from 4 electron pairs shared between the carbon and the hydrogen. So we looked at every element. Carbon had 4 dots, hydrogen had 1 dot, so we shared the 4 dots of carbon and the 1 dot of hydrogen. We made the hydrogen dot in red, the carbon 4 dots in blue, and that electron pair, and a second electron pair, and a third and a fourth adds up to 8 electrons, or an octet of electrons around carbon. So an octet of electrons is giving carbon a very stable configuration. Therefore, carbon goes ahead and forms 4 bonds. So according to Lewis, 1 electron pair is a single covalent bond. In this case, CH4 has 4 covalent bonds. We looked at NH3. We looked at the shape of CH4. What was the shape of CH4? Tetrahedral. So you had the carbon in the middle, HH. The angles were 109. We looked at NH3. Hydrogen still has 1 red dot, meaning 1 electron, 1 dot shared, and nitrogen is bringing 5. So you share the 5 of nitrogen. So you look in your chart. Again, nitrogen is group 5, so it has 5 dots. 1, 2, 3, 4, 5. And you're going to put a hydrogen in each one of these that are not paired. So you're going to put a hydrogen and a hydrogen and a hydrogen, giving nitrogen 2, 4, 6, 8, an octet. So yes, that fellow obeys the octet rule. It is not an exception. And it has how many covalent bonds? 1, 2, and 3. 3 covalent bonds and 1 lone pair. And the shape was not tetrahedral. Since you had a lone pair, it was pyramidal. Trigonal pyramid or pyramidal. Okay, so trigonal pyramid, like a little Egyptian pyramid. And the octet rule was obeyed. Then we looked at water. The angles for the pyramidal was 107. The angles here are 107. Okay. We still have how many electron pairs around the central atom? 1, 2, 3, 4. So we're still thinking 4 electron pairs around the central atom, and these 4 regions of negative density are going to point towards the vertex of a tetrahedron. So you have, for NH3, a lone pair where this white one is. This is a lone pair as opposed to having a hydrogen. So you only see the bottom part. That's a hydrogen, a hydrogen, and a hydrogen. So the angles here are 107 for NH3. You only see the little Egyptian pyramid here. That's one side, that's another side of your pyramid. Okay, so it's NH3 doesn't have this one here. This is a lone pair. And the angles here are 107. So this is trigonal pyramid or pyramidal. Yes, we remember this? Then keep reviewing water. Okay, we're going to talk in this lecture, besides the Lewis dots, we're going to talk about geometries, as I said earlier. And when we talk about geometry, we're going to look at 4 different regions of negative density here, meaning there's electronic geometry versus molecular geometry. Okay, so when I said that NH3 is pyramidal or trigonal pyramid, because this is what we see, the little pyramid, the nitrogen and the 3 H's, that's your little pyramid. That's one side of the pyramid, another side of the pyramid, and then back would be the third one. But we're also going to talk about electronic geometry. Okay, so if we could see electrons, which I know we can't, electrons are so tiny we cannot see them, but if we could see them, you will have 4 clouds of electrons around the nitrogen, and the electronic geometry would be tetrahedral. Okay, so the electronic geometry is as if I was looking at the gray sticks, and I have 1 gray stick, a second, a third, and a fourth. So the electronic geometry of NH3, electronic geometry, as opposed to molecular geometry. So we've seen of molecular geometry, that was pyramidal, but the electronic geometry is tetrahedral. Molecular geometry is trigonal pyramid. Okay, so what I am doing is I am using valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory. VSEPR, to predict the electronic and the molecular geometry. Okay, so tetrahedral is electronic geometry, because I have 1, 2, 3, 4 clouds negatively charged that repel each other, and they're going to want to be 109 degrees from one another. That's one thing. But then I consider the molecular geometry. And then I said, okay, let's get practical. I can't see electrons. I am only going to see the nitrogens and the 3 hydrogens. Those are my elements. And if I look at the molecular geometry, that's trigonal pyramid. That's pyramidal. Okay, so that's pyramidal. Okay, so in this chapter, in this lecture, besides Lewis dots, we're adding another layer to it, which talks about the molecular shapes, which we have seen a little bit, but we haven't seen electronic geometry at all. Okay, so I gave you a handout, yes? And in this handout, I am going to distinguish using valence shell electron pair repulsion the number of bonding pairs and lone pairs, and these are around the central element. Okay, so I look at my central element, and in the case of CH4, my central element is what? C. And I have 4 H's. So I have 4 bonding pairs. The electronic geometry is tetrahedral. The molecular geometry is also tetrahedral. They're both the same. So if I don't have any lone pairs, the electronic and the molecular are the same. But in the case of NH3, okay, so we did this. In the case of NH3, I do have a lone pair. I have my nitrogen HHH, so I have a lone pair. So my electronic geometry is still tetrahedral. I have 4 clouds of electrons pointing towards the end, the vertex of a tetrahedron, but I only have 3 H's, a nitrogen HHH. So the shape, the molecular geometry is pyramidal. Okay, the next one that we saw was water. What was water? Water was V-shaped. But we first look, okay, hydrogen has 1 dot, oxygen has 6 dots, so we first do Lewis. Before we use VSEPR, before we talk about electronic and molecular geometry, Lewis comes first. We must first draw Lewis. 2 hydrogens, and those are my 2 red dots, meaning the 2 valence electrons that hydrogen, the only electron that hydrogen has. And oxygen has 6. 1, 2, 3, 4, 5, 6. Are we okay with Lewis of water? Does Lewis obey the octet? Yes or no? Yes, it obeys because the oxygen has 2, 4, 6, 8 electrons around the central atom. Oxygen. How many bonds do we have? No, we have 4 electron clouds. But how many bonds? Bonding pairs. 2 bonding pairs. 1 here and 1 here. And the other 2 pairs are lone pairs. So we have 2 covalent bonds. These are my bonding pairs. 2 bonding pairs. And 2 lone pairs. So 2 plus 2 is 4. I have 4 clouds negatively charged around the central atom, and they will point towards the vertex of a tetrahedron. Okay, so I will have my oxygen in the middle, and my 2 hydrogens around it. A hydrogen here, and another hydrogen here, and my 2 lone pairs. So the shape of water, molecular shape, is V-shape, or bend, or angular. But the electronic geometry of water is what? Tetrahedral. Are we okay so far? So CH4, NH3, H2O, they all have the same electronic geometry because they all have 4 clouds of electrons around the central atom. Are you with me? Shapes is one of those topics that some students can't relate to, so I brought the model. I'm showing you on the screen, but whether I have a carbon in the center and 4 H's here, or a nitrogen here and nothing comes out. A nitrogen and HHH, I still have 4 sticks. So my electronic geometry is tetrahedral. And water, now I have 2 lone pairs. Only the white and the yellow, the white and the green on the bottom is what I see. So I see an angular. I see a V shape. I see a bend. But if I look at my sticks, my electronic geometry is tetrahedral. Yes? Are we okay with that? Okay. We did CO2 was, I think, our next one. After water, we did CO2 or CS2. Carbon has 4, oxygen or sulfur or selenium. They will have 6. And what was the Lewis dot structure for that? Okay, so first we do Lewis. And you do trial and error, or you can snap it. Share is needed minus available is what we did. Now I'm adding to this. Besides Lewis being this structure, so carbon, is carbon obeying the octet? Yes, I have 4 here and 4 more, that's 8. Is sulfur obeying the octet? 4 and 4 more is 8. So this fellow is okay with the octet rule. CS2 or CO2, they both obey the octet rule. But now we look at electronic and molecular geometry. Do I have any lone pairs here? No. So how many regions negatively charged do I have around the central atom? This is my central atom, thank you. Anybody else needs to sign the class roll? So I have 2 regions. This fellow is negatively charged, and so is that. And the angle is 180. Okay, so this is in your notes. So I have no lone pair, so electronic geometry and molecular geometry is the same. What shape do you think this is? Linear. Okay, so if I go back to my VSEPR, I am going to have CO2, bone pairs and lone pairs, 2. I have no lone pairs. I only have 2 bonds. I don't care if it's a single bond or a double. I don't care if I have 1 electron pair or 2 or 3, but I have 1 region of negatively charged pointing east and 1 pointing west. So 1 plus 1 is 2. So CO2, or actually BeCl2, do all the other ones for homework, are also linear. Electronic geometry linear, molecular geometry linear. Are we okay with CO2, molecular and electronic geometry? Okay, so CO2 obeys the octet rule. And we had done, I believe, carbonate and SO2. We did both of these. Is that true? Let's see if I remember, if my memory serves me correctly. Oh, we did SO3. Okay, so we did SO3. Let's go ahead and do SO2. Let's change this a bit. First thing we need to do is Lewis. And okay, so in order for me to determine geometry, molecular geometry or electronic geometry, I can't do anything unless my Lewis dot's on the table. SO2 is called what? Sulfur dioxide. Okay, so that's step 1. I do my Lewis, and I go 1, 2, 3, 4, 5, 6. And then I put my 2 oxygens. My oxygen number 1 or my oxygen number 2. I'll just go ahead and do Lewis really quick to get. I'm going to put oxygen with red dots. If this oxygen has 6, and I do the same thing here, what's going to happen? 1, 2, 3, 4, 5, 6. Is sulfur ever going to achieve the octet? No. So what do I need to do? Remove these 2, any 2, and share them. So I'm going to have a double bond on a single bond on a lone pair. Okay, so after I do my Lewis, I go back to my handout. Sulfur's in the middle, sulfur's there. Then I have an oxygen and an oxygen. the electronic geometry for SO2 is what? Trigonal planar. So all these guys are trigonal planars. Electronic geometry. Trigonal planar. But what I see is the sulfur and the two oxygens. So what do I have? A V shape. So the molecular geometry, if I have a lone pair, I said, okay, it's not going to be a flat triangle like this is. It is going to have a lone pair, so I only see an angular bend or B shape. Okay, let's look at some examples which do not obey the octet rule. Okay, so we have PCl5 we'll do first, SF4, ICl3, XCF2, SF6, so we have a few. We have like a good 7 more examples coming. And again, this table is backwards. They're telling you the shape. They're not even doing Lewis. In order for us to understand this table, because you need to understand what this table is telling you, you need to first do Lewis, and then from Lewis you do the shape. Okay, so everything's so logical here because they're telling you the answer. But that's not necessarily how it works. Okay, so I'm going to go first. Exceptions of the octet rule is when I have 5 electron pairs around the central atom. That's 10 electrons. That's not an octet. And another series of exceptions of the octet rule is when I have 6 electron pairs around the central atom. Okay, so all these will have 6. I'm going to go to a trigonal pyramid series first. Trigonal pyramid like PCl5. So if I ask you, what is the electronic geometry? What is the molecular geometry of PCl5? And I have PCl5 under my analysis, and the first thing I have to do is what? What do I first do to answer this? I don't know this. Okay, so I'm not looking at my handout. My handout has my questions. This is a question in a test. Either molecular geometry or electronic geometry. So I have to do first what? Lewis. Whichever way you may. You snap it, you do trial and error. Then you count the number of electron pairs, meaning bonding pairs, lone pairs, around the central atom. Okay, and if the count was 2, it's linear. If the count was 3, it's triangular. If the count was 4, it's tetrahedral. So we'll see what this looks like. I have PCl5, and I'll just slap them any which way they may. We said if chlorine or bromine or iodine or fluorine are present, we're going to treat them just like hydrogen. Remember? Hydrogen had 1 dot and it shared it. Well, chlorine has 7 and it's going to share the 7th. This chlorine has 7 and it's going to share the 7th. This chlorine has 7 and it's going to share the 7th. This chlorine has 7 and it's going to share the 7th. So I treat all my halogens. I don't care if it's F, Cl, Br, I, just like I treated H. H is above group 7, not because it's group 7 element, not H is not a halogen, but there's a lot of patterns, a lot of similarities in the way that their electrons are going to be bonding to other elements. Okay, so hydrogen only forms 1 bond, so does fluorine, chlorine, bromine, iodine. So you shared your peripheral dots. And then you go phosphorus. What group is phosphorus? 5, so it's going to bring 5. And we'll make them blue. 1, 2, 3, 4, and 5. So I did Lewis. Is this obeying the octet rule? Yes or no? No? This doesn't obey the octet rule, so now I have an exception to the octet rule. So besides all the examples that we've seen in the last couple lectures that obey the octet rule, there's many compounds that don't obey the octet rule. I count, and then I think, okay, I have 5 regions around the central atom, and they all repel each other. How can I arrange this? So this is what I'm going to do. I'm going to put a triangle on a chlorine up and a chlorine left. Okay, so I'm going to stand that up. PCl bond on top, PCl bond on the bottom, and then a triangle with a bond to every one of the 5 CLs. This is called a trigonal pyramid. I have a pyramid on top and another pyramid on the bottom. It's a pyramid, but it's on the north and the south of the equator being the triangle. What are the angles between that chlorine and that chlorine? That's what? That's a straight line. So what is that angle? 180. What is the angle between this chlorine, this phosphorus, and this chlorine? No. This is a triangle. So it's 120. 120 and 120 and 120 gives you 360, the whole circumference. Okay? So in a trigonal bipyramid, I have my phosphorus in the center, chlorine, chlorine, chlorine in my plane, and 1 Cl up and 1 Cl down, and I'll show you the model. Okay, so I have my phosphorus in the center, my 3 chlorines in my triangle. So you see your triangle there, 1 chlorine up, 1 chlorine down. The angle here between this chlorine, this phosphorus, and this chlorine is 180. The angles in that triangle is what? 120, 120, and 120. So this is a trigonal bipyramid. Any lone pairs in here? No. So electronic geometry, now I can answer. So I cannot answer electronic geometries until Lewis has not been addressed. And this is one exception of the octet rule. Electronic geometry and molecular geometry, they're both trigonal bipyramid. Or trigonal bipyramidal. I have a pyramid. If you look at this top white and this 3, that's a pyramid, and that's another pyramid. Do we see it? Okay, let's keep moving down the chart. We are going to do SF4, ICL3, SA. Okay, so I'm going down this route, and then we will continue to do a few more. So SF4. Same question. Give me electronic geometry, molecular geometry. What do I first do? SF4. SF4. Lewis. Sulfur in the middle. Fluorine, 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 and nothing else. Okay, so let's move them a little bit. Make them a little bit more symmetrical, because that's what we're going to try to do. Something like that. Fluorine, just like chlorine. Chlorine, fluorine, or hydrogen. They're all going to share 1. So we share 1. 1. The other 6 are not shared. Fluorine is group 7, so it has 7 dots. 2, 4, 6, 7. And sulfur. How many does sulfur bring? Look in your chart. Sulfur 6. I'll make sulfur red. Maybe. 1 for you, 2, 3, 4, and then what? 5, 6. So wherever you have a little room, just put another pair, because you need to draw Lewis. And sulfur has 6 dots, and fluorine, they all have 7 dots. So you share them. Does this structure obey the octet rule? Nope, it does not obey the octet rule. So I'm thinking I have 5 groups of electrons around the central atom. Let's clean it up. I have my sulfur in the middle, fluorine, 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 bond there, bond there, bond there, bond there, and a lone pair. Okay, electronic geometry. If I look at the electron density, 1, 2, 3, 4, 5. Electronic geometry is what? Trigonal bipyramid. I didn't change anything. But do I see a trigonal bipyramid? Do I have 5 fluorines? No, I don't. I see a trigonal bipyramid if I look at my electrons, on my bonds. But electrons are not visible. They're just pointing the angles. And what do I have here? This is my trigonal bipyramid. And now I'm going to get rid of one of these. So if I get rid of one of these, what do I see? This is like a seesaw. This is a fluorine, this is a fluorine, 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 and that is my seesaw. Okay, this is also called a distorted tetrahedron. This is my tetrahedron. 1 carbon and 4 H's, that was tetrahedron. 4 bonds. This is, if the white and the green are pointing towards that wall, like these 2 whites are, and the orange and the brown are pointing to the ceiling, that. Okay, so if I was to push those that way, that would be a tetrahedron. Okay, so it's called seesaw or distorted tetrahedron, and that's what this little drawing, this is a seesaw. This is your seesaw. Okay, so you have your sulfur, fluorine, 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 fluorine. Electronic geometry, trigonal bipyramid. All of these have trigonal bipyramid electronic geometry. But the molecular geometry, okay, so molecular geometry is seesaw or distorted tetrahedron. Okay, let's keep going. ICL3. Okay, so what's the first thing that we do? Same question. What's the electronic geometry? What's the molecular geometry for ICL3? I draw Lewis. That's step 1. Okay, so by all means, practice Lewis, because Lewis, there's going to be still another layer. After molecular geometry and electronic geometry, we're going to talk about polarity of molecules. Okay, so we can't do polarity of molecules unless we know the geometries, molecular and electronic. And we cannot do electronic or molecular unless we know how to do Lewis. So it's a series. You can't get to step 3 unless step 1 and 2 have been addressed. Okay, so in ICL3, I'm going to put a Cl, a Cl, and a Cl. Wherever. Just 3 Cls. They're all group 7, so they all have 7 electrons, and they're sharing the 7th one. 7, 2, 4, 6, 7. And my iodine, I'll do red. 1, 2, 3, 4, 5, 6, 7. Okay, so Lewis has been done. Is this structure obeying the octet rule? Nope. I have 5 groups of electrons hating each other, repelling each other. Negative repels negative. That want to be as far apart from each other as possible. So the electronic geometry, if I'm looking at that, I have a triangle here, one up, one down. Okay, so we'll clean it up. I has a CL, a CL, and a CL, a bond, a bond, a bond, a lone pair, and a lone pair. So what shape is this, guys? Electronic geometry, electronic geometry. Trigonal bipyramid. It hasn't changed. Electronic geometry is trigonal bipyramid. But do I see a trigonal bipyramid? No. I only see that CL, that CL, that CL, and they're pointing where? That's like a T. That's my T. So it's T shape. Are we okay with T shape? So I'm going to go back to my table. And ICL3 is T shape. XEF2. Let's understand XEF2. Okay, so we don't have to memorize this table. We just need to know how to do Lewis. And if we know how to do Lewis and we know how to count, we're okay. And when I say XECL2, I could have said XEF2, XEI2. Same question. Find electronic geometry, find molecular geometry. So I first do Lewis. And I'm going to put a CL and a CL. Okay, so I first do Lewis. Can't get out of there. Chlorine has groups 7 electrons, 2, 4, 6, 7. Xenon has how many? 8. So Xenon's going to give him 1, 2, 3, 4, 5, 6, 7, 8. So if you have 8, you write 8 dots. So the electronic geometry, still trigonal bipyramid. I'm going to have a chlorine there, a chlorine there, a lone pair, and a lone pair. So if I'm looking at my electron densities, it's still trigonal bipyramid. Okay, so electronic geometry, trigonal bipyramid. Are we okay with that? Not so bad? What about the molecular geometry? What do I actually see? I see a line, yes. So the molecular geometry, it's called linear. We don't call it a line, we call it linear. But the angles are what? 180. Okay. Not so bad. So we all counted 5, and the minute we count 5, we think trigonal bipyramid. This is what comes to mind. Okay, and if we have 3 lone pairs, my plane is where the lone pairs appear, not up and down. And my plane, because these are squished, so they're out of there. They're crowded. Okay, so I put a chlorine here and a chlorine here, and my xenon in the middle. And I just see that linear structure. This I can't see because they're only electrons. Are we okay? Are you following? Any questions so far? Okay, I'm down. You all have this handout, right? I'm down last line. We're going to now do SF6, ICL5, XZF5. So whether my question is, how many bonding pairs? How many lone pairs? What is the Lewis dot structure? Or what is the molecular geometry? Or what is the electronic geometry? Any of those questions, what do I have to do? Lewis. SF6. SF6. So I write a sulfur and fluorines everywhere. Fluorine, 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 fluorine. Just around Draw the most symmetrical structure. Look at each element in the periodic chart. Find your dots for each element, which is the group number. Sulfur is group 6. Fluorine is group 7. So sulfur has 6 dots. Fluorine has 7. And then you share them to see how many bonds you're going to end up. Okay, how many bonding pairs? These are your bonds. How many lone pairs? Okay, so I go, fluorine is 7, so it's 2, 4, 6, 7. 2, 4, 6, 7. We don't need to snap any of these guys because these are, if sulfur and fluorine are the ones considered, fluorine is a halogen, this is going to share one, period. You don't need to find out how many it's going to share. It's always going to share one electron pair. And then sulfur is my central, is group 6, so it has 6. 1, 2, 3, 4, 5, and 6. So I now did Lewis. That was step 1. This is always step 1. How many bonding pairs? How many lone pairs? 6 bonding, 0 lone. So I have 6 negatively charged clouds that repel each other. And they're going to point where? Okay, so let's clean it up a little bit. S. I'm going to draw a square. 1 up, 1 down. So it's another very symmetrical structure. And this is called what? Octahedral. And that's a D. Octahedral. And this is what an octahedral looks like. You have a square in the middle, 1 up, 1 down, and it's totally symmetrical. This could be my 1 up, 1 down, and that could be my square. This could be my 1 up, 1 down, and that could be my square. They're all what? 90 degrees, and from here to here, I have what? 180. Okay, so once we know what an octahedral looks like, we don't need this paper. Oh yeah, that's 90 and 180. We know what we mean. And the angles here are 90. The angles here are 90. The angles here is 180. Okay, so bonding pairs, 6. Does this structure obey the octet rule? 6 times 2 is 12. No way, Jose. Let's do ICL5 and XCF4. Unless you want other ones. ICL5. Okay, so if your question is again, how many bonding pairs? How many lone pairs? What is the Lewis dot structure? What is the electronic geometry? What is the molecular geometry? Any of those questions starts with Lewis. So Lewis step 1. And then we count to determine the electronic geometry, to determine the molecular geometry. Okay, and I'm picking CLs and Fs and Is. So by now, we should be like so comfortable. Iodine, 1 CL, another CL, 1, 2, 3, 4, 5. And bottom line, chlorine has 7, yes? And it shares the 7, so I'm going to go 2, 4, 6, 7, 2, 4, 6, 7, 2, 4, 6, 7, 2, 4, 6, 7, 2, 4, 6, 7. Share the 7th one. And iodine is also 7. 1, 2, 3, 4, 5, 6, and 7. Okay, so hopefully by now, after so many dozens of examples that we've done, Lewis is not a problem. Lewis is the simplest bonding theory. There are others that are not as simple. Does this structure obey the octet rule? No. I have how many bonding pairs? How many lone pairs? 1. So I have a total of 6 clouds of electrons hating each other, repelling each other. So it's octahedral. So I'm going to think putting a square in the plane, 1 up, 1 down. That's my octahedral. And then one of these is a lone pair. Put it anywhere because it doesn't matter. I'm just putting my lone pair there. And in all the other places, I'm going to put a chlorine, a chlorine, a chlorine, a chlorine, and a chlorine. The angle between this chlorine and that chlorine, that's 90 degrees. The angle between that chlorine and that chlorine is 180. Okay, so I have my octahedral, but I'm missing 1. It doesn't matter which one. Let's get rid of my yellow one. What do I have there? It's just a pyramid because I don't have anything down here. I just have a pyramid, but my base is not a triangle. My base is, yeah, my bases are always flat. But it's not a triangle, it's a square. So it's a square pyramid. You can connect that top with these 4. You get a pyramid. Okay, so let me do this. Let me change my lone pair since it doesn't matter for you to see the pyramid. Let me put my lone pair here. And let me put my bond there. I think that's easier to see. Okay, so your pyramid is there. Okay, so electronic geometry, what? Octahedral. But the molecular geometry is just square pyramid. Square pyramidal. Okay, so you think of your octahedron and chop out 1 bond and just make it a lone pair. So where my hand is, where the yellow is. Questions in here? Are you with me so far? Is this making sense? And we walk through XCF4. XCF4. XEF4. And again, your question could be, how many bonding pairs? Or how many lone pairs? Or what's Lewis? Or what is the electronic geometry? Or what is the molecular geometry? Or what's the polarity of this molecule? That's coming. I'm going to go back to the first one and talk about polarity. So we're going to add one more layer. So I start with Lewis. Xenon, F, 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 F. Just write 4 fluorines. And each one of them is going to share how many? Fluorines are sharing how many electrons? They have 7 and they share 1. So the other 7 I don't care about. The other 6 I don't care about, sorry. They share 1. The other 6 are not shared. Only 1 is shared. 2, 4, 6, and the 7th one's shared. And xenon is group. What group is xenon? 8. 1, 2, 3, 4, and then what? 5, 6, 7, 8. So I have this big mess of dots. Does this structure obey the octet rule? Nope, it doesn't. It doesn't obey the octet rule. Because you have 12 electrons around the central atom, not 8. Have 6 electron pairs. So how many bonding pairs? How many lone pairs? Bonding pairs? 4. Lone pairs? 2. So how do you arrange this? You do a little square, 1 lone pair, and another lone pair. So you have a bond, a bond, a bond, a bond. And that's a flat structure. Okay, so what is the electronic geometry? Octahedral. Okay, so the minute you have 4 plus 2, 6. The minute you have 6 groups of electrons negatively charged around the central atom, the electronic geometry is octahedral. Is this making sense? Do we see the pattern? Molecular geometry. It's just square. We don't have a pyramid. This screen, or this piece of paper that you're writing, you can have your xenon in the middle of the paper and fluorines at each corner of your paper. That's as flat can be. Okay? So it's square, planar, if you want to make a point out of that. Let me give you one more. BF3. And then we're going to do polarity, because that polarity just fits right where everything we've said. BF3, quickly. Electronic and molecular geometry for BF3. Now we know we need to do Lewis and fluorines in the picture, and fluorines sharing what? 1, the other 6. He's keeping all the other 6. Selfish little fluorine. Boron. How many for boron? Boron has 3, so the central atom is bringing in 3. Does this structure obey the octet rule? Nope. And remember that, because some structures have too many, but some structures have too few. And fluorines do not double bond. They don't do that. So I have a boron, 3 fluorines. We clean it up, draw the bonds. How many bonding pairs do I have? How many lone pairs do I have? 0. It's around the central atom. These are not lone pairs. Are we okay? So what do I have here? Trigonal planar. I have a little triangle. Are we okay with electronic geometry equal to molecular geometry, which are trigonal planar? Planar means it's just a triangle, and the angles are 120. 120 and 120 and 120. So you have 360. Questions in any of these? Okay, so let's add one more layer and then we'll be done. This little lecture on Lewis dot took us places. Lewis dots has been addressed. If to this I am going to add a question like, is a molecule polar versus non-polar? Okay, if my bonds are polar, we did that. We have 2 electronegative elements bonded to a non-electronegative element like oxygen bonded to 2 hydrogens. Oxygen very electronegative, hydrogen is not. We have 2 polar bonds because one electronegative element is pulling that cloud. Okay, so a polar bond is not the same thing as a polar molecule. Sometimes you have polar bonds and the whole molecule is polar. Sometimes you have polar bonds and the whole molecule is non-polar. Okay, so if they're asking you whether your molecule is polar or not, and again, day 1 in 1046 they start here because they have many layers to add to here. You say, okay, what is my structure? Is CH4 polar or non-polar molecule? In order for a molecule to be polar, first do Lewis. You have 4 covalent bonds. These bonds are non-polar, and on top of that, this is totally symmetrical. Totally symmetrical. So whatever happens north is canceled with whatever's happening south or east or west. If I ask you, is CO2 or CO2 or CS2? I passed it. Polar or non-polar? Here we go. Is this molecule polar? Is this guy polar? CO2 or CS2? They're both going to be the same answer. What do you think? You do Lewis, and this is your Lewis. Okay, so Lewis step 1 for a polarity of molecules. And then you go, okay, my molecular shape was what? Linear. I don't have any lone pairs. I have a bond, and whether I have carbon, oxygen, oxygen, or carbon, sulfur, sulfur, that's a polar bond. I'm going to have a dipole pointing east and a dipole pointing west. But the dipole, if I have a sulfur at each end of the carbon, is pulling with the exact same intensity. So I have like a tug of war. This dipole is with the exact same magnitude and opposite inside than that one. So my net dipole is 0. So I have polar bonds here, which I had seen that before, because sulfur or oxygen are more electronegative than carbon. But since I have one pointing east and one pointing west, the whole molecule is non-polar molecule. Do you follow me? Okay, so this has polar bonds, and the whole thing is non-polar. What about the one that we just finished doing? Geometries. We just finished doing BCl3, BF3. What do I have here? So my question is this a polar molecule? Is this polar or non-polar? You do Lewis, we do shapes, and we know that this is, okay, so first Lewis, then shapes, and then I go, is this bond polar? You bet. If fluorine's there, that's going to be a polar bond. You're going to have a dipole there, and a dipole there, and a dipole there. So all three bonds are very polar. But is the whole molecule polar? No, it's totally symmetrical. So if you have a very symmetrical molecule, I don't care if it's linear, I don't care if it's triangular, or tetrahedral, or trigonal bipyramid, or octahedral. If you have the exact same thing at each vertex, each dipole is going to cancel the next one. Okay, so the whole molecule polar? No, non-polar molecule. Remember vectors? If you add these two vectors, you get this, and that will cancel that. Okay? What about, let's go back to geometries. Geometries up. Is this molecule polar? What do you think? SF6. This molecule? No, that molecule is non-polar because it's totally symmetrical, and whatever happens north is canceling east, west, south. Okay, so that's non-polar molecules, although all the bonds are polar. What about ICl5? Is that molecule polar? Whoa. ICl5. Yes, I have a lone pair. So I have a region, this bottom region, that's slightly negative. So that is not totally symmetrical. That is a polar molecule. So many times, if I have a lone pair in a tetrahedron, or if I have like an ammonia, that's going to be polar. Two lone pairs in a tetrahedron like water, that's going to be polar. Okay, so if I have a tetrahedron, this guy, yes, it's polar. This guy, yes, it's polar. This guy, no, non-polar, totally symmetrical. This guy, non-polar. This guy, yes, it's polar. What about this guy? Slightly negative, so this region is slightly negative, and this is not. So what? Major polar. Okay, what about this guy? Polar. What about this guy? Non-polar. Okay, so polarity can only be understood after Lewis and after shapes have been addressed. Have a wonderful Thanksgiving. I'll see you next time.